All right, today's focus is on scientific notation. And as you discovered in class, scientific notation is used for writing very, very large numbers and for writing very, very small numbers. Now, there's a specific process for writing numbers in scientific notation. We want our value that we're going to write in scientific notation to be less than 10, and we want it to be greater than 1. Now, yes, it can be 1. No, it cannot be 2. So let's say it this way. Greater than or equal to 1, but less than 10. Now, every scientific notation problem has the format, whatever this number is getting multiplied by 10 to a certain power. Oh, come on. All right. So again, whatever the number is, times 10 to a certain power. So obviously we need a little bit more understanding of scientific notation. It's a little bit easier to explain what this means when we're actually using a number. So let's start with our first example. The Amazon rainforest covers 2,500,000 square miles. So the first thing we want to do is figure out, using 2,500,000, how we can create a number that is greater than or equal to 1, but less than 10. So we're going to start up here at the front and chunk out everything that's not a 0. And put a decimal after the first term. 2.5. Now, is 2.5 greater than or equal to 1? Sure it is. Is it less than 10? Absolutely. So we've already qualified the first statement. So then we are going to multiply. And since we're on the screen and it's got lots of image in the back, I'm going to go ahead and use a multiplication symbol that is looking like an X. No, that's not a variable X. I'm just saying multiply. It's actually more common to see the multiplication symbol like this with scientific notation. Even though by the time you hit 7th grade, we generally say, stop using that multiplication symbol. Use the standard dot so that you're not confusing it with the variable X. But typical way to see it is this way right here. So we have 2.5 times 10 to a particular value. Well, we want to ask ourselves, if I had 2.5, how many times would I have to multiply 2.5 by 10 to get 2,500,000? Well, the quantity of times that we would have to multiply it by 10 is the number of times we would move the decimal place. Because remember, when you multiply by 10, it moves the decimal one value over. When we multiply by 10 again, it moves the value 1 over. When we multiply by 10, it moves the value 1 over. So we've already moved 1, 2, 3, 4, 5, 6 times. So 2.5 times 10 to the 6th power miles squared. That is our scientific notation. All right, let's try another one. The Amazon rainforest has over 40,000 different, those are in the reverse order, 40,000 different plant species. So again, we want a value that is greater than or equal to 1, but less than 10. We're going to multiply it by 10 raised to a particular value. Let's see, how many times do I have to move the decimal from here to here? That would be 1, 2, 3, 4 times. So 4 times 10 to the 4th power. Now, one of the things I want you to go ahead and start picking up on is that when we're transferring from standard notation to scientific notation, we are moving the decimal to the left. And when we move the decimal to the left, it is creating a power here that is going to be positive. That will come into play as we get later in the week. All right, now we want to model in standard notation. Notice that you have been given scientific notation, and we want to convert it to standard notation or expanded form. So the number that we start with that's greater than or equal to 1 but less than 10 is 7.5. And so I could certainly write 7.5. And then we see that I'm moving the decimal place 2 times. Now, the nice thing about 10 squared is we know that 10 squared is 100. And this is not the first time that you have ever multiplied a value by 100. You know that if you multiply 7.5 times 100, which is the same as changing a percent, right? That we would move the decimal over 2 places. Well, our decimal needs to fall right there. So what happens with our empty space here? You're right. It's going to end up becoming a 0. So our final solution, 750 types of trees. All right. Ooh, what in the world is that? E. Never seen that before. Well, if you've ever used a calculator and gotten a really large or a really small number, you have ended up with E on the calculator. And so I need for you to be familiar with what we consider calculator notation. Now, the E in calculator notation. The E in calculator notation is the times 10 to a particular value. The value after E is that exponential value. So notice, transferring from calculator notation to standard notation or even to scientific notation is not that big of a deal. So our leading value that's greater than or equal to 1 but less than 10 is going to be 3. So we now have 3 times 10 to the third power. So 3, where the decimal is going to move to the right 3 spaces, 2, 3 spaces. And we need to fill each one of these with zeros. And so there are now 3,000 types of fruit. Model in standard notation. It is estimated that 2.0 times 10 to the 4th square miles of the Amazon rainforest are destroyed each year. Well, 2.0 is our number that's greater than or equal to 1 but less than 10. So we have 2.0 where the decimal is getting moved 4 places. 1, 2, 3, 4. And so we now have the number 20,000 miles squared. Now, at this point in time, I want you to start picking up on the fact that when our scientific notation gives us a positive power, in order to create a standard notation, we are going to move the decimal to the right 4 units. Well, when we're in standard notation and we are converting to scientific notation, we move the decimal to the left 4 units and it results in a positive power. Why? Because each time we multiply by 10, it makes our number larger. So 2 times 10 becomes 20. 20 times 10 becomes 200. 200 times 10 becomes 2,000. 2,000 times 10 becomes 20,000. Well, how many times did I multiply the value by 10? 1 time, 2 times, 3 times, 4 times. So the more times you multiply a number by 10, the more zeros it's going to have added to it. All right. Writing in scientific notation. There are 7,500 species of butterflies in the Amazon. So we first want to find our value between or greater than or equal to 1, but less than 10. That would be 7.5 times 10 to a particular number. How many times did we move the decimal? 1, 2, 3 times. All right. Now, all of those were examples of numbers that were really large. What about when you have information that's really small? Like maybe the leafcutter ant, which is about 0.51 inches long. Remember that our first term needs to be greater than or equal to 1, but less than 10. So we want to take this number and figure out, well, if I move the decimal over one place, now all of a sudden I have the number 5.1, where my where my term is greater than or equal to 1, but less than 10. And we're going to multiply that by 10. Well, that doesn't quite sound right, Mr. Gable. If you multiply 5.1 times 10, you're going to get 51, not 0.51. Well, that's true, isn't it? So instead of multiplying by 10, we really want to divide by 10. 5.1 divided by 10. Oops. Now, this changes things up just a little bit, because 5.1 divided by 10 is actually going to move the decimal backwards, which is what we want it to do. But we need to remember something about our exponent laws to understand why that 10 is now in the denominator. If I give you the number 10 and I want to bring that number down into the denominator, remember from our exponent laws that we had to have a negative power. 10 by itself has a positive power, but if I make 10 have a negative 1 power, that's going to give me 1 over 10 as a solution. Well, then all of a sudden, if I multiply 5.1 times 1 over 10, we end up with 5.1 over 10, which is going to simplify to our given starting solution. That answers a lot for us, doesn't it? We don't really want to multiply by 10 to the first power, which is going to give us 51, but rather we want to multiply by 10 to the negative first power. So this is where we start to think of, okay, the powers. When we're going from standard notation to scientific notation, and we move the decimal to the left, we'll have a positive power. When we are going from standard notation to scientific notation, and we move the decimal to the right, we need to have a negative power. So 5.1 times 10 to the negative first inches. Now, yes, I realize that 0.51 inches is not that small of a number. This was just a simple example for us to go ahead and get an indication of what happens when we multiply by 10 or when we multiply by 10 to the negative first power, so that you could easily understand what was taking place. Here's a little bit of a smaller number. All right, this is the world's largest freshwater fish. It's found in the Amazon. It can grow to 0.0025 kilometers long and weighs 250 kilograms. I want us to write the 0.0025 kilometers in scientific notation. So I'm going to be moving the decimal 1, 2, 3 units to the right to get the value 2.5 times 10. Now again, we know that if I if I multiply 2.5 times 10, I'm going to get 25, which is going in the wrong direction. So I don't want to multiply by 10 to a positive power, but rather to a negative power. At this point, we just need to know what negative power. Well, how many times did we move the decimal? We moved it 1, 2, 3 times. So 2.5 times 10 to the negative third kilometers long. Now, while we're on this page, let's go ahead and look at the weight. Could we write that in scientific notation as well? Sure, we could. We'd move 2 decimal places over, and we would end up with 2.5 times 10. We move the decimal 2 places to the left, and so we're going to end up with 2.5 times 10 to the second power kilograms. Let's see if you can give this one a shot. I'm going to pause for just a second, or you'll pause the video for just a second. Solve the problem, and then come back and check your answer. All right, a poison dart frog weighs around 0.0088 pounds. We want to write it in scientific notation. So we're going to move the decimal until we create a number greater than or equal to 1, but less than 10. Well, that would be right here. By the time I move the decimal to there, I end up with the value 8.8 times 10. Well, if I multiply 8.8 times 10, I get 88. That's going in the wrong direction, which automatically tells me we need to have a negative power. Now, how many times do I need to multiply that by our negative power? 1, 2, 3 times. So we end up with 8.8 times 10 to the negative third power pounds. How'd we do? Let's try one more. A squirrel monkey is 2.5 times 10 to the negative 4 kilometers long. This is equivalent to 25 centimeters long. I would like for you to write the 2.5 times 10 to the negative 4th kilometers in standard notation. All right, welcome back. So we have the 2.5 getting multiplied by 10 to the negative 4th power. Well, that negative 4th power tells me we're really dividing 2.5 times 10 to the 4th power, which is going to make 2.5 very small. So instead of moving our decimal to the right for multiplying by 10, since we're multiplying by a negative power, we're going to move the decimal to the left. 1, 2, 3, 4. Now that we've moved to the left 4 units, we want to fill each one of these spaces with a 0. And as I've told you before, I want to know for sure that is a decimal, not a booger, not a piece of jelly from the toast you were eating, Not a random smudge that was on your camera, but a decimal. So you're going to put a 0 in front of the decimal, a 0 after the decimal. So our solution will be 0.00025. Now, there's something interesting on the screen now. Take just a second, see if you can see an interesting pattern between what we started with and what we ended with. If you haven't had enough time, press pause. Hopefully, you are noticing the pattern that when we have a negative power, we have an equivalent number of zeros to match that power. That's an interesting observation. That actually makes it really easy to go from scientific notation to standard notation if I know that I'm going to need 1, 2, 3, 4 zeros, and then I just write down my number. Now, it's a bit of a shortcut, and you always want to be able to rely on your understanding of the math concept, but it works. It's a pattern. Model in standard notation. The water lily is one of the largest flowers in the Amazon rainforest. Its leaves can be up to 6 feet in diameter. This is equal to 1.1 e to the negative 3 miles. Who remembers what that e is? If you said that E represents calculator notation, you are absolutely correct. That E tells me that we're going to have times 10 to the negative third power. Well, let's drop down the rest of our value. And we have a negative third power going to standard notation. So I need 3 zeros followed by my term, decimal place, miles. All right, can we check this to make sure it ended up with that solution? Sure. 1, 2, 3 places it took to move over between 1.1 times 10. We moved to the right 3 places, negative 3. We did just fine. Again, if you need to, and I'm fine with this, you can always take your 1.1 and move it back 1, 2, 3 spaces. So we're going to have a decimal there and a 0 in front of it. I am fine with either process. Again, if you see the pattern that a negative power is going to end up with an equal number of zeros, that saves you some time. Model in standard notation. A tiger's tooth is about 2.5 inches long. This is around 7 times 10 to the negative second yards long. I want you to convert the 7 times 10 to the negative second yards long into into standard notation. All right, so again, using our pattern process, I see I'm going to have 2 zeros and a 7 with a decimal between the 2 zeros. 0.07 yards. Write the number in both scientific and calculator notation. So I want you to pause the video, write this in scientific and calculator notation, and then when you're ready, come back and check the solution. A large tarantula is about 0.583 feet. Yummy. Now in scientific notation, we're going to move the decimal over 1 place. So we will have 5 times 10. All right, we're moving over 1 place, which means we have a positive power. Oh, sorry. Why did I leave off the rest of the number? 5.83 times 10. All right, we move to the right from standard, which means we actually have a negative power. Because if I multiplied 5.83 times 10, that's going to move the decimal one more to the right. That doesn't help me out at all. In order to get back to what we started with in standard form, I need to multiply or divide by 10 to move it back to the left. Okay, so we now have 5.83e negative 1. So we have our scientific notation, and we have our calculator notation.